In the previous lecture, we have started to discuss the Euler's equations. You know, actually Euler's equations are the equations of motion of a rigid body. And in that lecture, you have seen a particular method known as Newtonian method to derive this Euler's equation of motion. And as I have told you that there are two methods to obtain the Euler's equations. The second one is known as Lagrange method. So as we have already discussed Newtonian method to obtain the Euler's equations, so today we will see how we can derive Euler's equations of motion for a rigid body by Lagrange method, or you can say that by the Lagrangian formulation of mechanics. Okay. Now, as we have seen in the first lecture, that Euler's equation deals with the motion of a rigid body when the body is fixed at one point and a torque is applied on it. And you know, when a rigid body will be fixed at one point and a torque will be applied on the body, then only the rotational motion of the body is possible. And as in case of rotational motion of a rigid body, you know, the three suitable generalized coordinates are Euler's angles, which are denoted by the symbol phi, theta and psi. You have already discussed this. In case of rotational motion of a body, the most suitable candidate for the generalized coordinates for the system are what? They are Euler's angles. Okay? Because these Euler's angles phi, theta and psi completely describe the orientation of the body which rotates. Okay? Therefore, in this discussion, we will have to select the generalized coordinates. And can you say what will be the most suitable and most convenient generalized coordinates in this case? Definitely, the three Euler's angles phi, theta and psi will be the most suitable set of generalized coordinates. Okay? Because we are considering the situation when the rigid body is in rotational motion only under a torque. So definitely you will have to select the generalized coordinates phi, theta and psi, which are called Euler's angles. And you have a concrete idea of Euler's angles as you have seen these things in your previous lecture. Okay. Now we will consider the conservative system. You know, a conservative system means a system which performs its motion under conservative forces. Okay. And in this case, if you are talking about the conservative system, how the Lagrangian of the system will be defined? You know, Lagrangian L is defined as T minus V, where you know T is the kinetic energy and V is the potential energy of the system. Here we are talking about the rotational motion of the rigid body. So here this T means rotational kinetic energy. Okay. Now since the most suitable generalized coordinates are phi, theta and psi. So I have written the first generalized coordinate q1 is phi, second generalized coordinate q2 is theta and the third generalized coordinate q3 is psi. Okay. So in this case, definitely the Lagrangian L will be a function of these three generalized coordinates phi, theta and psi. Okay, as the potential energy will be also a function of phi, theta and psi, and this kinetic energy is also a function of phi, theta and psi. But in this expression for Lagrangian in equation 1, I have written in this in the argument of kinetic energy T phi dot theta dot psi dot 2, because you know Lagrangian is a function of generalized velocity and generalized coordinates. Here phi, theta and psi are generalized coordinates, and phi dot, which means del phi by del t, theta dot, which is del theta by del t, and psi dot, which is del psi by del t, these are the generalized velocities corresponding to the generalized coordinates phi, theta and psi. So some student get confused that how we can say that Lagrangian is only a function of phi, theta and psi. When you say generalized coordinate, that means independent variables, independent coordinates. Actually, these phi dot, theta dot and psi dot are not independent variables. They ultimately depend on phi, theta and psi. That's why we simply say that kinetic energy in this case is also a function of phi, theta and psi, and the potential energy is also a function of phi, theta and psi. So that this Lagrangian L, you can say, is a function of the generalized coordinates phi, theta and psi, which are Euler's angles. Okay. Now, for our discussion, since the body is rotating about a fixed point situated in the body, and we consider an instantaneous axis passing through that body, as you have learned earlier, so it will be more convenient to discuss the motion in body set of axes. Okay. And for simplicity and convenience, we also take that body axes are the principal axis. Okay. So if you will talk about the principal axis, then what is the expression for the kinetic energy T? You have already learned in my previous video the detailed discussion of the rotational kinetic energy, and you have seen that the rotational kinetic energy in terms of the principal body's principal axis is given by this expression. This is 1 over 2 I1 omega 1 square plus I2 omega 2 square plus I3 omega 3 square. Here you know I1, I2 and I3, these are the principal moment of inertia of the body, which means these are moment of inertia of the body about the three principal axes, that is x-axis, y-axis and z-axis, or you can say first principal axis, second principal axis and third principal axis. Okay. And omega 1, omega 2 and omega 3, these are the components of the angular velocity vector along the three principal axes respectively. Okay. Now since T is equal to this much, which I have defined in this equation 1a, so the expression for Lagrangian L can be written as L equal to 1 over 2 I1 omega 1 square plus I2 omega 2 square plus I3 omega 3 square. This is at the place of T, and minus V of phi, theta, psi. Okay. Now since we are talking about the Lagrange method of obtaining Euler's equation, so we will have to write the Lagrange equation of motion for a conservative system. And you have seen the Lagrangian formulation of mechanics earlier in my videos, and you know the Lagrange equation of motion for a conservative system is written as d dt del L by del qk dot, okay, or qk dot minus del L by del qk equal to 0. Okay. This is Lagrange equations of motion for a conservative system. Here you know qk are actually the generalized coordinates and qk dot are generalized velocity. Here there are three generalized coordinates phi, theta and psi. Okay. So first of all we will write the Lagrange equation of motion for any one generalized coordinate, and for convenience first of all we select psi as the generalized coordinate to write down the Lagrange equation. You may write this equation for phi or theta, any one. when we will write the Lagrange equation for the generalized coordinate psi, that is the third Euler angle, which is rotation about the z-axis, then we will get one of the Euler's equation. You will see later on. And after that, by inspection, by the permutation, we can write the other two equations, because you have seen in my first video on this Euler's equation, there are three Euler's equations for the three components of torque acting on the body along the three body axes or three principal axes. Okay. So now let us write Lagrange equation for coordinate psi. So at the place of this qk, now we will write psi. So Lagrange equation for coordinate psi is written as d dt del L by del psi dot minus del L by del psi equal to 0. Okay. But L is equal to T minus V. Okay. So you can replace L by T minus V in this equation. So you can see L is equal to T minus V. So I have replaced L by T minus V in Lagrange equation. So this Lagrange equation becomes d dt del T minus V by del psi dot, this is psi dot, okay, minus del psi T minus V, and that will be equal to 0. Okay. Now this operator del psi dot will be operated on T and V both. Okay. And when you will actually operate it on V, then del V by del psi dot, this will be 0. Why this is 0? Because you know, for a conservative system, the potential function does not depend on the generalized velocity. It depends on generalized coordinate only. So the partial derivative of this potential function with respect to the generalized velocity psi dot will be equal to 0. So I have not written it here. So instead of this del T minus V by del psi dot, there will be only del T by del psi dot. Okay. And in the second term, there will be minus del T by del psi plus del V by del psi. Minus minus will become plus. And I have actually brought that term in RHS, so there will be, this will be equal to minus del V by del psi. So this is the Lagrange equation with respect to the generalized coordinate psi in terms of kinetic energy and potential energy. Okay. Now you know this psi is the third Euler angle, and third Euler angle you have already learnt earlier. What is this angle? Actually this psi is the angle of rotation about the principal z axis. You know, you have already learnt. And so the angular velocity with respect to this generalized coordinate, which will be denoted by the symbol omega psi, that will be psi dot. This is d psi by dt or del psi by del t. Okay. And in this case, what will be the generalized force? Actually here, at the place of generalized force, there will be the z component of impressed torque. If you are forgetting the concept of generalized force, watch my video on Lagrangian formulation, where I have discussed independently the concept of generalized force, and there you will find that the torque may be a generalized force, okay, whose dimensions are not equal to ml2 t inverse 2, ml t inverse 2. Okay. So in this case, the z component of the torque, which is written by tau 3 or tau z, okay, instead of z I have written 3 subscript tau 3, which is actually the generalized force q psi. And you know that since the system is a conservative system, so this generalized force will be equal to negative gradient of the potential function. And since generalized force for a conservative system is negative gradient of potential function. So this tau 3 will be equal to minus del V by del psi. Minus del V by del psi. This is negative gradient of potential energy function with respect to the generalized coordinate psi. And that will be equal to tau 3 because psi is the third generalized coordinate, and so which is actually the rotation about the z axis or third principal axis, and so we get the generalized coordinate tau 3. Okay. So in this equation 3 you can see, since in RHS this term minus del V by del psi is present, but we have recognized now that this minus del V by del psi is what? This is the Z component of the applied force, applied torque on the body. So instead of minus del V by del psi in equation 3, now you can write tau 3. Okay. So now this Lagrange equation defined in equation 3 can be written like this. Tau 3 equal to, I have written actually this tau 3 in LHS, that will be equal to d dt del t by del psi dot minus del t by del psi. Okay. I hope the calculation is not tedious and you can easily understand it, and so if you will watch the video seriously, each and every step will be clear to you. Okay. So now let us see. As here we are talking about the kinetic energy function whose partial derivative with respect to the generalized velocity psi dot and psi has been taken here. But in general, the kinetic energy directly depend on the components of angular velocity, and that angular velocity depends on the generalized coordinate. Okay. So this del t by del psi dot, this can be written like this. This is tau 3 equal to d dt summation over I del t by del omega I times del omega I by del psi dot. T is a function of function. T directly depends on angular velocity, and angular velocity depends on this psi dot. And minus, instead of del t by del psi, you can write summation over I, where I actually runs from 1 to 3. 1 to 3. Okay. And this is del t by del omega I times del omega I by del psi. You can actually expand this summation, that will be del t by del omega 1 by del psi dot plus del t by del omega 2 times del omega 2 by del psi dot plus del t by del omega 3 times del omega 3 by del psi dot. And in the same manner this second term can be expanded. Okay. But you know, kinetic energy, which I have already defined here, you can see this kinetic energy is given like this, and in compact form this expression for kinetic energy you can write that T is equal to 1 over 2 summation I 1 to 3, okay, I omega I square. That is same expression. Okay. And therefore del t by del omega I, this will be what? When you will differentiate this, this will be equal to I omega I. Okay. I omega I. And therefore, yes, I have only considered del t by del omega I, so summation sign is not present here. Okay. After differentiation, this will be 2 omega I, and that 2 will be cancelled, and result will be I times omega I. Okay. Now see, this for here you can see that if you will take sign of summation here, then there will be also sign of summation here, okay, for I. Okay. Now, actually, in my previous lecture, I have provided a video completely on the angular velocity of a rigid body, in which we have discussed how we can find the components of angular velocity with respect to the body set of x's and the space set of x's. And I have told you that the results of components of angular velocity of a rigid body with respect to the body set of x's are more useful, because that will be needed in the several concepts which we will discuss further. Now you can see here we need it, and I have told you earlier that you must remember those results. So you have seen in my previous video that the first component of the angular velocity vector omega, which is denoted by the symbol omega 1 or omega x, which is actually the x component with respect to the first body axis, okay, and that is given like this. This is phi dot sine theta sine psi plus theta dot cos psi. I have written this result here directly because I have already taught you earlier, and you must remember these things, okay. How this result comes, you have learnt earlier, okay. I am writing it here directly, okay. Now omega 2, which is equivalent to omega y, this is given by phi dot sine theta cos psi minus theta dot sine psi, okay, and omega 3, which is equivalent to omega z, this is given as phi dot cos theta plus psi dot. Can you remember these results? You have already studied earlier. Now, for finding this tau 3, our aim is to evaluate tau 3, which will be the one of the Euler's equations. For this, you can see we need the expression for del t by del omega I, okay, del t by del omega I. And when you say del t by del omega I, it means there will be three values: del t by del omega 1, del t by del omega 2, and del t by del omega 3, okay. And we also need the value of del omega I by del psi dot. Psi dot means generalized velocity, and omega I will have three values, for three values of I, omega 1, omega 2, and omega 3. So let us evaluate from this equation 6 the values of del omega I by del psi dot, okay. And you can see from here that del omega 1 by del psi dot, what will be that? You can see, since the expression for omega 1 does not contain psi dot, so you can say that omega 1 does not depend explicitly on psi dot. It depends on psi, it depends on theta, it depends on phi dot, it depends on theta dot, but not on psi dot. So its partial derivative with respect to psi dot will be equal to 0. And similarly, you can also see that this omega 2 is also not an explicit function of psi dot. Therefore, the partial derivative of omega 2 with respect to psi dot will be also 0. Have you understand? Definitely you have understand. Now, see the expression for omega 3. Omega 3 depends explicitly on psi dot, because in the expression of omega 3 you can see here psi dot is present. So del omega 3 by del psi dot, what will be that? Since the first term is independent of psi dot, so its derivative will be 0. But when you will differentiate this psi dot with respect to psi dot, that will be 1. Therefore, del omega 3 by del psi dot, this is equal to 1. Okay. Now, we will substitute all these values in this equation 5. to get the value of tau 3. So let us see. We have obtained the value of this del t by del omega I times del omega I by del psi dot with summation over I. First of all, let us evaluate all the terms, and after that we will put the values in this equation 5. Okay. So let us see. Summation over I, where I runs from 1 to 3, del t by del omega I by del psi dot. What will be this? When you will expand, this will become del t by del omega 1 when you take I equal to 1 times del omega 1 by del psi dot plus del t by del omega 2 times del omega 2 by del psi dot. Here I have taken I equal to 2, and del t by del omega 3 times del omega 3 by del psi dot. But you can see this del omega 1 by del psi dot is 0 and del omega 2 by del psi dot is also 0. So this first term is 0, second term is also 0. But del omega 3 by del psi dot, you can see this is equal to 1. Okay. So this is equal to 1. Okay. And if it is 1, then result is simply equal to del t by del omega 3. Del t by del omega 3. And what will be del t by del omega 3? From this equation, you can see that del t by del omega 3 will be simply equal to I3 omega 3. You will put, if you don't write here the sign of summation, then you can easily understand it. If you omit this sign of summation, you can easily understand. Del t by del omega 3, you will take I equal to 3. So that will be I3 omega 3. Or you can also see this expression, which is not in summation form. When you will differentiate this t, that is equation 1a, with respect to omega 3 partially, then the derivative of first two term will vanish and only there will be 2I3 omega 3, and this 2 will cancel and result will be I3 omega 3. Okay. So you can see that okay. So this del t by del omega 3 will be equal to I3 omega 3. Okay. I3 omega 3. In this way, we have obtained this term, first term, not first term, but the bracketed term. Here d dt is present. Okay. Now we will evaluate the second term of the equation 5. And for this, again we will see this equation number 6. And as here omega I has been differentiated partially with respect to psi, so we will differentiate this omega 1, omega 2 and omega 3 with respect to psi. Okay. See the expression. When you will differentiate this omega 1 with respect to psi partially, what will be the result? Here phi dot sine theta will be treated as a constant factor, and the derivative of sine psi with respect to psi will be cos psi. Okay. And for this cos psi, this will be minus sine psi. So del omega 1 by del psi, this will be what? This is phi dot sine theta cos psi minus theta dot sine psi. But see the expression for omega 2. Omega 2 is this much, and this is just equal to what del omega 1 by del psi. You can see. So this is equal to omega 2. Okay. Now differentiate this omega 2 with respect to psi. See the expression. When you will differentiate this, phi dot sine theta will remain at each, and the derivative of cos psi will be minus sine psi, okay, and that of sine psi will be cos psi. So this will be minus phi dot sine theta sine psi minus theta dot sine psi, and when you will take minus sine as a common factor, the remaining factor will be just this much, and therefore that will be equal to minus omega 1. You can see this is equal to minus omega 1. So del omega 2 by del psi is equal to minus omega 1. Okay. Now see the expression for omega 3 and differentiate this omega 3 with respect to psi. Is psi present in the expression for omega 3? Answer is no. Here psi dot is present, not psi. So you can say that omega 3 is not an explicit function of psi, and therefore its partial derivative with respect to psi will be 0. Okay. So you can see I have written this del omega 3 by del psi is equal to 0. This is equal to 0. Okay. So in this way we have obtained the first and the partial derivative terms of the equation 5, and therefore now you can obtain the value of this much, which is the second term of the equation number 5. You can see this is the second term. We have already obtained this bracketed the term inside this square bracket, okay, and now we are going to evaluate this second term of equation 5. Okay. Now you know summation over I del t by del omega I times del omega I by del psi, when it will be expanded, what will be this? This will be del t by del omega 1 times del omega 1 by del psi plus del t by del omega 2 times del omega 2 by del psi plus del t by del omega 3 del omega 3 by del psi. Now let us substitute the values of del omega 1 by del psi, del omega 2 by del psi, and del omega 3 by del psi from here, which we have obtained already. You can see del omega 1 by del psi, this is omega 2. So instead of this del omega 1 by del psi, now I have written this omega 2. And again you know del t by del omega 1. What is this? Expression for t, you know this is 1 over 2 I1 omega 1 square plus 1 over 2 I2 omega 2 square plus 1 over 2 I3 omega 3 square. Okay. So when you will differentiate this t partially with respect to omega 1, the derivative of the second and third term will be 0, and that of the first term will be I omega 1. So instead of del t by del omega 1, I have written I1 omega 1. Okay. And instead of del omega 1 by del psi, you can see this is omega 2. So the first term becomes I1 times omega 1 times omega 2. Again you can see from here, when you will differentiate this t with respect to omega 2, that will be I2 omega 2. Okay. And del omega 2 by del psi, this is minus omega 1, as you can see here. So the second term becomes I2 omega 2 times minus omega 1. Okay. But del omega 3 by del psi, this is 0. Therefore the third term vanishes. This is del t by del omega 3, this will be I3 omega 3 at times 0. So this will be 0. Now if you will take minus here as a common factor, minus 1 as a common factor, then this becomes I minus I2 minus I1 times omega 1 times omega 2. Okay. So in this way we have evaluated the value of this term, which is the second term in RHS of equation 5. So now we will use this equation 8 and the equation number and this equation number 7. Equation 7 and equation 8 we will use in the RHS of this equation 5. See, okay. So what will be now tau 3? After using these two equations, you can easily say, so tau 3 will become d dt. D dt was present there, you have seen. I3 omega 3 at for the expression inside the square bracket, you have seen this is equal to I3 omega 3, as you can see it here, okay. And at the place of second term, we will write minus I2 minus I1 by 1 times omega 1 omega 2. But since minus sign is already present here in the before the second term, so minus minus will become plus, okay. So this is what? This is plus I2 minus I1 times omega 1 omega 2, okay. And here I3, you know, it is time independent, so differentiation will be only of omega 3. So this will be tau 3 equal to I3 d omega 3 by dt, and d omega 3 by dt is written as omega 3 dot. So tau 3 is equal to what? This is equal to I3 omega 3 dot plus I2 minus I1 times omega 1 omega 2, okay. After seeing this equation, what you are thinking? Have you seen this equation earlier? Definitely, if you have watched the previous video, that is the Newtonian method for the deduction of Euler's equation, then you can think that this is nothing, this is simply the third Euler equation, okay. So in this way, by Lagrangian approach, we have derived the third Euler's equation because we have selected the third Euler angle as generalized coordinate, okay. So in the similar manner, when the other two generalized coordinates phi and theta will be taken as the generalized coordinate and set up the Lagrangian equation, then we will get the other two equations. But there is no need for that. You can write the other two Euler's equation by inspection, simply by the cyclic permutation of the indices. And for this, let us see, I am just giving you a trick. When you write the third component, that is tau 3, then in first term, the indices will be 3. That will be I3 omega 3 dot here. So when you will write tau 1, there will be I1 omega 1 dot, okay. Now see the second term. When tau 3 you have written, then mark, in the second term the index 3 will not present. Only the first and 1 and 2 indices will be present. And so there will be I2 minus I1. Here one thing also, you may be confused. We will write I2 minus I1 is here. Then here what will be? I2 minus I3 or I3 minus I2. So actually in first term of the determinant, when you have found the omega cross L, then the first term of determinant is positive, third term of determinant is positive, and the second term is negative. So in make a trick that we have to subtract the smaller indices from the larger indices. So there will be I3 minus I2, not I2 minus I3. Have you understand? And here in the subscript of omega will be this 2 and 3, okay. But as the second term of determinant is negative, so here that rule will not obeyed, that will be just reverse. Here you will not write I3 minus I1, but I will write I1 minus I3. And tau 2, This will be I2 omega 2 dot plus I1 minus I3 omega 3 omega 1. So these are the Euler's equation which we have obtained in today's lecture by the Lagrange method using the Lagrange equations of motion. So in this way you can see that first of all we have obtained the third Euler's equation, which is just identical to the Z equation which we have obtained in Newtonian method. Actually the other two equations, as I have told you, can be obtained simply by the permutation of indices. Okay, and we are justified in doing so due to the fact that identification of one of the principal axes as z-axis is entirely arbitrary. You can take x-axis as z-axis, you can take y-axis as z-axis. It is arbitrary. Okay, therefore if you have obtained the Euler's equation for z considering the z-axis, then in the similar manner you can obtain the Euler's equation considering the x and y axis. Okay, but it should be emphasized, however, that these two equations shall not be generalized equations for theta and psi coordinate, theta and phi coordinate. Okay, so after these two lectures, I hope you have clearly understand what are Euler's equations of motion. Actually, in these two lectures, we have only derived the Euler's equation, not we have seen its applications. But in our forthcoming lectures, you will see the applications of this Euler's equation, because Euler's equation of motion are the basic or the fundamental equations of motion for dealing with the motion of a rigid body which rotates when one of its point is fixed. Okay. Thank you very much.